Example 12. This problem differs from example 11 because in example 11 we were solving for Ka. In example 12 we're solving for pH. So here we go. Similar to the last problem, we cannot just use our traditional formulas to find answers here, to find pH, because we have a weak acid. So we will need to use an ice chart. So we're going to set up our acid, showing it acting as an acid or dissociating or breaking down. And then we're going to set up ice. Let's see what we have. So we have, remember, I stands for initial change equilibrium. We're given a Ka value, therefore we know something at equilibrium, and we know an initial concentration. This time we're given it straightforward. We won't have to calculate moles over liters from the mass. We are given the, remember, big M stands for concentration, and it's the concentration of this acid when at equilibrium. So we can plug that in, and we know then initially, just like before, we have zero amount initially of H plus or C6H4O2N minus concentration. And then we know that as time goes on, we're going to increase on the product side and decrease on the reactant side. So this is minus X on the reactant side right here, and plus 1X and plus 1X. Remember, the 1 represents that it's a 1 to 1 to 1 ratio. If there was any kind of balancing that occurred where there was coefficients, we'd change the number in front of X. So far, we don't have any of those. And then, so we know now that our E will be I plus C. Okay, I went ahead and did the expression. I have this value given to me. I know I got to get this. And I want to see what I need to do going forward with this. I need to figure out this concentration. So I know then that Ka is 1.4 times 10 to the negative fifth. I got that from the given and to me in the problem, and it is Ka at equilibrium. So I can set my expression up, and then I can plug in my pieces of ice. I went ahead and did my E now. Remember, E is I plus C. And when I plug that into here, oops, that's going to be my next slide. When I plug that into here, I get X over X, because remember 0 plus 1X, this would be, these two would be X. That's where I get this and this from here and from here. And then this is 0.1 minus X. That would be set equal to, and I don't know if let me see if I did that. I did. So that would be set equal to this part right here, X squared. So I don't know about you, but right now you'd be like, what? Because that's going to be an X squared over something with an X. So that means we're going to have to do the quadratic formula. And, you know, we don't want to do that. So us chemists, us scientists say, is there any way we can avoid the quadratic formula? No offense to math teachers, but we have a lot of math we do all day long. We don't want to do the quadratic formula. So what we're going to do is we're going to be able to apply something called the 5% rule. This allows us to make a few assumptions. 5% rule says the amount of acid that reacts is assumed to be so negligible that it in the subtraction from its original amount of acid if no more than 5% of the acid reacts. That's a lot of words. Let me kind of give it to you in my own phrasing. That was a definition I got online. So what it basically means is that the 5% rule means that X is so small it doesn't impact the 0.1 value. So we assume 0.1 minus X to be 0.1. So what I'm saying, what we're trying to say by the 5% rule, we're going to have to validate it, that this X would be so small it doesn't change this. It basically stays 0.1, which is fantastic because if we use that 5% rule, and we have to verify, if we use it, we have to verify that it was okay to use, meaning that our we have 5% of it, and I'll show you that in just a minute. Then we can go down here and get rid of this, saying it's so small that we can do this. Now this is very manageable problem. We don't have to do a quadratic because we only have X in one spot, right? And I don't have it in multiple spots that can't be combined without using the quadratic formula. So I'm going to solve this for X by multiplying both sides. Put this over 1 if that helps you. Cross multiply. I get X squared equals 0.14 times 10 to the negative 6. I take the square root of both sides and I get 1.18 times 10 to the negative third. So that's still the 5% rule definition down there. Now, we can use this X and go forward with this in the next step. Let me show you what we're going to do next. So we're going to verify that this works before we go further. So to do the 5% rule verification, we're going to take our X value, divide it by the assumed concentration. So here's the X value, and here's the assumed concentration. That means the part without the X when we did that up here. times 100. When I do this, I get 1.18%, which is less than 5%, so we're allowed to use the 5% rule. So once we verify the 5% rule, and yes, you'll be required to verify, then we can proceed on. So now we know that this x that we just solved for represents the x here, right? So this, remember, this was just x. It's 0 plus 1x, so this would be 1.18, and that's what we need. We need H plus concentration to solve for pH. And then, yeah, this would be 1.18 times 10 to the negative third, and this would be 0.1 minus 1.18 times 10 to the third. So if we put in our calculator 0.1 minus 1.18 to the 3 negative, I still get 0.1 for my answer. That's why we can use that. Okay, so then because I need to figure out pH, I'm in search of H plus at equilibrium. Remember, pH is at equilibrium. So I figured out that I have 1.18 times 10 to the negative third would be x here, and then we showed here that that would be negligible. So I'm plugging it in here into my formula. pH is equal to the negative log of H plus concentration. That's the formula that we traditionally, algebra formula, that we traditionally get to use and have used with strong acids. But now that we have a weak acid, we have to go through these ice charts. And so here we are. So we're going to take this, plug in our X value for H plus, because we already showed that it represents H plus at equilibrium. And we get a pH of 2.928 for our pH. Thank you.